While a wooden table feels solid to the touch, it is functionally 99% empty space. The atoms that compose it are vast voids, with nearly all their substance concentrated at a single central point. If you enlarged an atom to the size of a classroom, that central nucleus would be no larger than a pinhead. Despite its size, that pinhead contains more than 99.9% of the atom's total mass. The nucleus is composed of nucleons, positively charged protons, and the neutral neutrons first identified by James Chadwick in 1932. To understand the behavior of matter, we must look past the empty space of the atom and into the dense mechanics of the nucleus itself. Density inside the nucleus reaches 2.3 times 10 to the 17th power kilograms per cubic meter. This is the same density found in a neutron star, an object so compressed that a single teaspoon of its material would weigh billions of tons. Because the nucleus is packed with positively charged protons, electrical repulsion should theoretically drive these particles apart. Stability is maintained by the strong nuclear force. This short-range attraction peaks at 0.8 femtometers, providing enough pull to overcome the electrical repulsion of the protons. The nucleus exists as a structure under immense internal pressure, held together by the strongest force in the physical world. We can test the consistency of nuclear matter using an oxygen-16 nucleus, which contains exactly 8 protons and 8 neutrons. Summing the individual weights of these 16 particles gives an expected mass of 16.12744 atomic mass units. Yet a fully assembled oxygen-16 nucleus weighs only 15.99053 units. This difference of 0.13691 units is known as the mass defect. In the assembly of a nucleus, the total mass of the system is consistently lower than the sum of its individual parts. Albert Einstein's mass-energy equivalence explains where that missing matter goes. Einstein demonstrated that mass is a highly concentrated form of energy, and the two are interchangeable via the relation E equals mc squared. The missing mass converts directly into the binding energy that holds the protons and neutrons together. For oxygen-16, that 0.13 unit mass defect equates to a release of 127.5 mega-electron volts. Binding energy serves as a direct measure of stability. The more mass that is lost during assembly, the more tightly the nucleus is held together. The binding energy curve maps the stability of all known elements by plotting energy per nucleon against mass. The peak is iron 56. At 8.75 mega-electron volts per nucleon, it is the most stable nucleus in nature. Heavy atoms like uranium occupy the lower slope on the right. When they split into smaller, more stable fragments, they move up the curve and release energy through fission. On the left, light nuclei like hydrogen move up a much steeper slope when they fuse into heavier systems, releasing even more energy through the process of fusion. Every reaction in a star or a reactor is an attempt by atoms to reach a more stable state at the peak of this curve. Chemical reactions, such as burning coal, involve energy changes in the range of single electron volts. Nuclear reactions involve mega-electron volts, a million-fold increase in energy per reaction. Fission of 1 kilogram of uranium generates 10 to the 14th power joules. Burning 1 kilogram of coal generates 10 to the 7th. The energy output of the sun is the result of hydrogen atoms undergoing this climb toward higher binding energy via fusion. Modern nuclear science focuses on replicating and controlling this process on Earth to provide a high-density energy source. The mass defect is the literal mechanism that converts matter into the energy observed in stars and reactors. It is the key to the energy potential within the atom.